For question 1, we're assuming that human body temperature is normally distributed with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62. So for part A, a hospital uses 100.6 as the lowest temperature to be considered a fever. So what percentage of healthy people would be considered to have a fever under this definition? So what's going on here is that because the mean is 98.2 and the standard deviation is 0.62, there's going to be some percent of people whose body temperature is greater than this, yet they're healthy. And the question is, well, is that a lot of people? Maybe that means we should reconsider this definition by either raising or lowering this temperature. So to analyze this, to determine this percentage, I'm going to use a bell-shaped curve since we're talking about a normal distribution. So there's my bell-shaped curve, and I'll draw a number line below it. Right here in the middle is our mean of 98.2 degrees. And I think the other important information to mark is going to be over here, which is 100.6. So 100.6 degrees Fahrenheit is some distance away from the mean. What we want to figure out is, what is this area? The area to the right of 100.6 represents the percentage of people whose body temperature is greater than 100.6, yet they're healthy. They do not have a fever. So I want to figure out what that is. And what we're going to do is we're going to normalize this data and basically use StatCrunch to figure out what the percent is equal to. So a little work ahead of time is I need a z-score. And I'm going to use this formula to figure it out. X minus mu over sigma. So both of these things are given information, and so is this as well. I put 100.6 in place of x, I subtract the mean, and divide by the standard deviation. That will normalize this data, allowing us to figure out the percentage. All right, so if I plug all this in, that's 100.6 minus 98.2, all divided by 0.62. I did this ahead of time, and my z-score was 3.87. Let me look that up. Yes. So what this tells me is, oh, that's a z-score that's really far away from the mean. It's almost 4 standard deviations away. So I'm expecting this to be a very small percentage. So the rest of this is just getting my answer by using StatCrunch. So I'm looking for the percentage of z-scores that are greater than 3.87. Now, it doesn't actually give me the percentage. It gives me its decimal equivalent. It gives me the probability. The value I got was 0.0001, and when I convert that to a percent, that's 0.01%. That is extremely small. So the second question here is, does this percentage suggest that the cutoff score is the cutoff temperature is appropriate? And I think you could argue this either way, but I'm going to say yes, it's appropriate because, I mean, you don't want to have a high percentage of people who are actually healthy, but you admit them for services. So I'm going to say yes, this is appropriate. There's not a lot of people who are going to have a temperature higher than 100.6 yet are healthy. So part B is addressing this similar question just in a different way. It says several physicians at the hospital want to lower the cutoff temperature. Perhaps they feel that this is too strict of a percentage. So, what temperature should they lower it to if they want to change this percentage from 0.01 to 5%? I mean, 5% is still really small, but maybe it's just a better temperature to use. All right, so to figure this out, I'm going to draw, again, a bell-shaped curve with a number line below it. I'll label the mean of 98.2, but this time I'm solving for some x. I'm solving for the x that corresponds to an area of 5%, or 0.05. All right, what we're going to do is figure out the z-score that corresponds to this percentage on the bell-shaped curve. Then we're going to use all of that information and this formula to solve for the corresponding x. If I can find the z-score, it means I know z. I already know mu and sigma. The only thing I won't know is x, but the x will represent some type of temperature. So let's write that out. So again, we're using z is equal to x minus mu over sigma. But we need to figure out, well, what is the z that corresponds to an area of 5%? This is a commonly used one. You can look it up if you'd like, but that is z is equal to 1.645. So all we need to do to answer this question is put all of the given information into this formula and solve for x. So let's do that. In place of z, I put 1.645. X is the thing I'm solving for. That's going to be the temperature that corresponds to that percentage. I subtract 98.2 and divide by 0.62. So a little bit of algebra here. All I need to do is solve this equation for x. I'll first multiply both sides by 0.62. All right, and I get 1.0199 is equal to x minus 98.2. I'm now going to add 98.2 to both sides. And when I do, I get 99.2199 is equal to x. And I mean, we could round this a little bit. I mean, we're going to be, I'd say, pretty close. Maybe I'll go to 2 decimal places, but I'll say 99.22 degrees Fahrenheit. That is the location on the axis here that would correspond to an area of 5%, as opposed to an area of 0.01%. Question 2 is also referring to a normal distribution, but this is now about SAT scores. So we're assuming that SAT scores are, of course, normally distributed with a mean of 1,060 and a standard deviation of 195. Part A is asking if one SAT score is selected at random, what is the probability that it is greater than a 1,500? So I think for all of these, it's just very useful to visualize it using a bell-shaped curve. That way you can mark on the axis, well, the center of the data is a 1060, and 1,500 is a good score. That's, way over here. So if you were to just randomly choose one SAT score, what's the likelihood that it's greater than a 1,500? So the area that we want is over here. So to do this, again, I'm going to use a z-score. So what I'll do is plug in place of x, 1,500. The mean is a 1060, and the standard deviation is 195. So let's directly plug those numbers in. Okay, and if I plug that into my calculator and simplify it, I get 2.26. So, okay, that's, over 2 standard deviations away from the mean. All right, now to figure out what the probability is, again, I'm doing this just directly by using StatCrunch. So I want the probability that we are greater than 2.26. All right, and when I get that value, I get 0.0119 approximately. And if you like think about it in terms of a percent, that's 1.19%. So 1,500 is a good score. I was expecting the percentage to be low, and it certainly was. All right, now part B is, again, somehow using this normal distribution, but it's just a slightly different type of question. All right, this one is saying, if we don't select one, but if we chose 20 SAT scores at random, what is the probability that they have a mean that's greater than 1,500? I would think this would be less likely than what we saw in part A. I'm expecting the percentage to be smaller. I mean, choosing one at random and getting a score greater than this was already pretty small. So if I picked 20, averaged all those scores, I would expect that value being greater than 1,500 to be, not likely at all. So what we're going to do to figure this out is use a formula. Okay, and that formula is a z-score given by this, x bar minus the mean all over the standard deviation divided by the square root of n. And we just have to appropriately choose or label all these different variables. Okay, so this represents the mean, and we're saying a mean of 1500. So it's not just one score now. Like up here, this x meant was just one that was greater than 1500. Here, we're choosing 20 SAT scores, and we're saying we want the mean to be greater than this. So this is the mean of those 20 scores. We still have that the mean is a 1060 and that the standard deviation is 195, but here n represents the number of scores that you are choosing, which is 20. So we're going to do almost the same thing. Instead of using this formula, we're using this one, but once we get this value, our computation will be done in StatCrunch using something like this. So let's simplify this carefully. Z is equal to, okay, that's a 1500 minus a 1060, all divided by, okay, here we have 195 divided by the square root of 20. So I'm going to have to round this a little bit, but I just want to be careful with order of operations. I want to make sure that I first figure out that fraction in the denominator before dividing it into the numerator. All right, so z in the numerator, 1500 minus a 1060 is 440. And when I divided this out in my calculator, I got roughly 43.6. So let's double check that. 195 divided by the square root of 20. Yeah, I mean, I'm rounding it, but it's going to be a very good approximation. So when I now divide those two numbers in my calculator, I get, if I go to 2 decimal places, 10.09. All right, if I already know, like here was the z-score for the first one. It wasn't likely because I was over 2 standard deviations away from the center. But this one, this z-score is over 10 standard deviations away from the center. We are very, very far away. So in StatCrunch, I want the probability that we're going to be more than 10 standard deviations away from the mean. And the value I get for this, the probability, it's very small. It's essentially 0, but 0.0001. So not very likely, and that is it for this question.